So now in this video, we are going to talk about the introduction to function notation. So hopefully you've watched the previous video on how to determine if something's a function, okay? So a function is something where your domain never repeats itself. So each domain value only shows up once. Now, once you determine if something's a function, you can actually represent that using function notation. And it's a new way to describe or name equations. So right now, you guys are super used to seeing this. Y equals 4x plus 3, okay? But function notation is a way more useful notation when describing an equation, okay? It allows us to mathematically describe a relation. Function notation allows us to describe the independent variable in terms of the dependent variables in terms of the independent variable. So this is what function notation is. And at first it can feel a little odd, but that's okay. So let's learn it together. A symbolic notation used for writing a function. So this weird little thing, you got to understand, is not f times x. This can be read in three different ways. This can be read as f of x. So this is f of x, or f at x, or f is a function of x. Okay, so that can be really confusing at first, but it's really crucial to understand. So you kind of want to start really using this terminology when you go through math. It is crucial to understand f and x are not multiplying each other. I cannot stress this enough. We are not multiplying f and x. You have to understand f is the name of your graph. F is the name of your graph. And x is the dependent variables in your graph. Okay, so we can look down here, function notation, a little example. This is representing f of x. And now here is your input value, also your domain value, also representing an independent variable. And f, this is your output. So f is also equal to 3x plus 1, okay? So 3x plus 1, this is a way, okay, I'm going to plug in a number at x, and I'm going to plug it into my equation. So instead of representing, remember that original equation we said, y equals 4x plus 3, I'm going to instead set that up as f of x equals 4x plus 3. My name of my equation is no longer y, it's actually known as f, or f of x. So name of graph. And again, x is my independent variable. And here, understand, f depends on x. Like here, y depends on x, but now we've changed it to be called f, and f depends on x. Let's see some examples as it kind of can help solidify the understanding. Okay, but just to understand, f and x are not multiplying. It's a notation thing. It's a new name. So let's get a handle simply notating relations that are functions. So state the following functions using function notation. How can we read the new equation? So here, instead of using y, I'm going to say y is equal to f of x. And f of x equals 5x minus 4. Okay, so how do I read this? I read this as f of x equals, and then simply 5x minus 4. Okay, another way to read this is understanding f is a function of x. Okay, and it is a function because we plug in x values here and it changes what f is. Something to always understand, you can always say f of x equals y. These are interchangeable. Okay, y and f of x are interchangeable. Now let's look over here. This changes things a little bit. Sometimes you're not always going to represent using y. Okay, when it's y, it's easiest to represent it with f of x. With c over here, recognize c is my dependent variable, right? Because c is determined by what p is. So we can plug numbers in for p and it changes what c is. Who decides what p is? Well, we do. So p is the independent variable because we decide what happens. We choose p, right? We can say p at 5, so on and so forth. So we could say like p equals 5. What is c? Well, then we just simply plug in p for 5. So that's some grade 9 questions. So it'd be 4 times 5 minus 7. That would be 20 minus 7. And 20 minus 7 gives us 13. Anyways, we need to represent this using function notation. So function notation, remember, we read it as, up here, f is a function of x. Well, here, c is a function of p. So c is described in terms of p. So there's our new definition. And we read this as c is a function of p. Which makes sense because c depends on p. Okay, c is chosen by p. If we plug in 4 for p, that changes what our c value is, just like we showed up here, but we're just using a different notation. Okay, so remember, this is not c times p, this is c as a function of p. Now, putting it into a real world context can be really helpful. Let's use this one. The following equation, c equals 5r plus 100, represents the cost. C dollars, so C is cost, and it's represented in money, dollars. And a carnival ride for every ride rode, R. So R equals rides taken. Okay, and there's no really unit for that. Now, right now, we just have C equals 5R plus 100, but we can be more descriptive using mathematical language. Okay, we can say in function notation, C is a function of R, and that function is 5R plus 100. So now we say C is a function of R. It's easier actually now because we actually have what C represents. We can say this, cost is a function of rides, which is totally true. Cost is a function of rides. We choose how many rides we take, and the amount we owe is based on the amount of rides we ride. Okay, so cost would be our our dependent variable. And rides is our independent variable. And remember, that's because we choose this. The cost is based on what we choose. Okay, so this is C is a function of R, and now we can represent it as cost is a function of rides, which is true. Cost is a function of rides. Cost depends on the amount of rides we do. And this relation explains it. So this, the outside thing in your function notation, is always the dependent variable, and inside is your independent variable. C is being described by R. Let's look at this one. So this is kind of a crazy looking equation here. This is the height of a rock thrown from a 7 meter, height. The height of a rock thrown from a 7 meter, let's put building there. Sorry about that, I missed that. Can be represented by the following equation, where h equals height in meters and t equals time. So remember, what are we trying to do? We're trying to state these in function notation. So here, if we think about it, how high we're going is dependent on the time at which we are talking about. So you don't have to understand how we get this equation or how we get this graph. This is actually Math 20-1 stuff, but it is useful to understand what the graph looks like. So the graph looks like this. Okay, where this is 7, and then so on and so forth. So this is 7 meters. And this is height over here, and this is time. Okay, so there's our graph. It looks something like that. Now we can see here that height of your rock does depend on the time at which we're talking about. Can we choose the time? Like, we don't have any control over time. So this is the independent variable. Remember, the independent variable is either the thing you can control, absolutely, or you have no control over and it just happens. Height depends on time. So this means it is the dependent variable. Dependent variable. So now I can represent this using function notation because height depends on time, aka height is a function of time. So instead of just writing h, I'm going to write h of t. Okay, and then this would equal t minus 3 squared plus 7. So here I'm representing, and how do I read this? I represent this as h is a function of time. Or as a function of t, sorry. Let's put t there. But I can plug in h for height because it's stated that h is height and t is time. So here I could say this. Height is a function of time. Another word to describe this is height depends on time. Okay, so that's how we describe function notation. Again, is this h times t? Not at all. This is just saying in a new name that h, which is this equation, depends on the time that you plug in. Okay, so definitely some new way of thinking about equations and how to name them. Okay, so let's maybe move on and actually learn how to utilize function notation. So mathematicians can utilize function notation to get away from long sentences, essentially. Instead of always having to describe things in words, we can just use function notation really easily. So for example here, determine what y is when x equals 2 for p equals 4x plus 2. That's a type of question that you would be able to answer by the time you finish grade 9. Okay, so here we simply just plug in x. We plug in 2 for x. Okay, here we can totally simplify it. Okay, if we use function notation. And so instead of representing p equals 4x plus 2, we can represent it as p of x. And now this equation, or this question, has now been simplified into if p of x equals 4x plus 2, find p at 2. So these guys are the same questions. Okay, these are the same questions. This is saying if p of x equals 4x plus 2, we've replaced the x with 2, so now replace 2 in wherever you see x. Okay, so it may be used to remember, and remember, this can also be represented as p at 2. So you can read p of 2 as p at 2. So what is p when 2 is x? Okay, so let's see some examples here. So the following equation, C equals 5R plus 100, represents the cost, C dollars at a carnival, for every ride rode on R. So we already talked about this. If we would describe this in function notation, it would be the cost is a function of R, and that equation is 5R plus 100. Okay, so this is a cost as a function of R. And we did that last page. Or you can say cost depends on rides. Okay, Now, here's us actually using function notation. Determine C of 3. What does it represent? So here it says determine C of 3. Notice what we did. We have taken our R value and replaced it with 3. That means we have to take 3 and plug it in wherever we see R in our equation. So C of R we know is 5R plus 100. We replaced R with 3, so now we take our 3 and replace it with R. So this will become 5 times 3 plus 100. Okay, and then we can start solving this. So this equals 5 times 3 is 15 plus 100, so that equals 115. And this would be C at 3. So here we can read this as, if we just have C at 3 equals 115, this would be the cost when 3 rides are taken, let's say road, the cost when 3 rides are rode is $115. Okay, so that's what this represents. C at 3 equals 115. So the cost at 3 rides is 115. Okay, so what does it represent? It represents the amount of money it costs to ride 3 rides. C at 3 represents the amount of money, or let's just say the cost, to ride 3 rides. So lots of different ways to kind of think about this, but it all represents the same thing. All of these sentences are saying the exact same thing. When you ride 3 rides, it costs $115. That is summed up in this single little notation. Okay. Now, here's where it gets a little tough. So it's kind of easy to understand that if you have a number replaced in with your whatever your independent variable is, that you just plug it into your equation. Now what happens when we want to determine the value of R that makes CR equal 115? What does this represent? So remember, our equation right now is the C as a function of R equals 5R plus 100. Okay, here we're saying find R when the cost is 115. So this is a question of saying what value of R makes C 115. Okay, because remember, this isn't two things multiplying. This whole equation is C, and it's in terms of R. That's what this means. This is the equation of C. Remember what equation we started with? C equals 5R plus 100. When we say this simply just means that our equation for C is an equation that uses the value R. Okay? So what do we do here to solve for R? Well, what we do here is we have to replace all of CR with 115. Okay, this time we're not placing R with 115. It's actually saying take CR and replace it with 115. So here, there's CR. So put 115 there. And that equals 5R plus 100. And now you're going to do some simple algebra. So we're going to subtract 100 from both sides. And that will give me 15 equals 5R. And then we're going to divide by 5. So here we get 15 divided by 5, 3 equals R. Okay, so essentially, just hang on a second. So here, we have learned that for the cost to total $115, we must ride 3 rides. And then you're done. So C of R, when C of R equals 115, R equals 3. Okay, let's do one more example, and then you can go practice. Okay, so using the relation y equals 3x minus 1, write the relation in function notation so that f is a function of x. Okay, recognize we always kind of just take what our number or what our dependent letter is, so h, and put it in terms of t. So h of t, c of r, okay, c of p, we can see that up there, but why do we not do y of x? You can technically do that, but it's usually not a smart idea. So here, if we follow the same thinking, we could put y of x equals 3x minus 1. Why do we not use this notation? Because this is really confusing. This is often why mathematicians, if they have a y, they just replace it with f, okay? Because putting y of x, that gets really confusing because this kind of seems like y times x, which is not what it's supposed to be. So whenever you have a y value, it's smart to just replace it with f. So here, we could say f of x equals 3x minus 1. And what mathematicians usually say is y equals f of x. They're the exact same thing, right? So y equals f of x. So now we've taken our equation and we've taken this relation and we have now stated it f as a function of x. So my f value is a function of x and this is the relation it's used. Now let's determine some values. So determine f at 3. So here, recognize, what have we replaced here? Well, we replaced the entire x value for 3. So this has become f at 3. And remember, this can be read as f at 3. So we're trying to figure out what is f when x equals 3. Remember that's a whole sentence right there. So now simply take your x value, wherever you see it in your equation, and replace it with 3. So I'm going to do 3 times 3 minus 1. So what did I do there? I replaced my x values that I see here with 3. Okay, and now I'm just solving this. Oh, sorry. So this is f at 3 equals, well, 3 times 3 is 9 minus 1. So f at 3 equals 8. So when x equals 3, y equals 8. And remember, that represents a coordinate point, 3 and 8. Remember, y has been replaced with f. So you can also say when x equals 3, f equals 8. Okay. So these, now we have solved. Okay, because remember, f and y are the same thing. Let's do one more here, c. So determine the value of x if f of x equals by 53. So this one, remember, we have an equation for f of x. F of x equals 3x minus 1. It wants us to find the value of x that makes this whole thing f of x equal 53. So I'm going to replace f of x with 53. So 53 equals 3x minus 1. And now we're going to solve. So I'm going to add 1 to both sides. And I'll get 54 equals 3x. And then I'm going to divide 3. And I'm going to end up getting x equaling 18. So remember, what did I say? Y equals f of x. So here, when f of x equals 53, x equals 18, stated below. You could also say when f equals 53, x equals 18. Or lastly, you could say when y equals 53, x equals 18. And these are all represented with a coordinate point where your domain is the first thing and then your range. Or your, sorry, these should be brackets, or your x coordinate or your y coordinate, or your independent coordinate and your dependent coordinate. What's my independent coordinate? Well, it's x. So 18, and my range coordinate in this case would be 53. So 18 and 53. Okay, so lots to kind of mull over in your brain. You really, really, really want to practice this, because if you don't understand how to use function notation and talk about it, it can be very, very tough moving forward. Okay, so make sure you give it a shot. Practice quite a few questions in 5.2, okay? Because moving forward, you want to know all of these terms. Okay, if you need help, please come in and we'll go through some examples together. Make sure you're using your textbook, and we'll go from there. Other than that, have a good day.